Welcome and thank you for joining. Let's take a look at question number 27 on page 84 from the textbook. For the power function f of x equals x to the power of n, we have to find the x-intercept of the tangent to its graph at point 1, 1. What happens to the x-intercept as n increases without bound or n approaches infinity, and then explain the result geometrically. So the first time we read the question, we just want to get a general idea of what it is about. Now we read it a second time with the intention to understand the information given, write it down and sort out what's given and what we're asked to find, and try to find the connection between the information given and what we are required to find. So let's read together again. For the power function f of x equals x to the power of n, it means that we are given the equation of some function in power form in this case, and we have to find the x-intercept of the tangent to its graph at point 1, 1. So we are drawing a tangent line on the graph of this function. A good equation to start with for the equation of the tangent will be equation of a line in slope y-intercept form, y equals mx plus b. Now we have to find the x-intercept of the tangent line. So I write this down here. That's what we need to find ultimately of the tangent. Now, the tangent line is drawn at the point 1, 1. So first we have to find what the x-intercept is. Now, in order to find the x-intercept of the tangent, we need to know the equation of the tangent. So let's take a look at the information that will help us find the equation of the tangent. So the tangent is drawn at the point 1, 1. Now remember that when we draw a tangent line on the graph of a function, the point of tangency is a point that belongs to both the graph of the function and the graph of the tangent or the tangent line. So what that means is that the coordinates of this point must satisfy both the equation of the function and the equation of the tangent. So what that means again is that if we substitute x equals 1, 1 into the equation of the function, I must make the equation true, and the same thing we can say about the equation of the tangent. So, and as you can see here, if x equals 1, 1 to the power of n would be equal to 1. So even if you were given just one of the coordinates, in this case would have been sufficient enough for us to figure out the other coordinate of the at the point of tangency. So in order to find the equation of the tangent, we're also going to need the slope. Now another word for slope is derivative. So, and that would be the derivative of the function where we are drawing the tangent at. So that means that the value of the slope would be f prime at 1. So that should take us back to the equation, and we have to find now the derivative of the function and evaluate it at 1. So if f of x equals x to the power of n, therefore f prime x would be equal to, just power rule, nx to the power of n minus 1. Now remember that we need to find the derivative exactly at x equals 1, because that would be the slope of the tangent. And that would be equal to coefficient n, x is 1, so we'll replace x by 1 to the power of n minus 1. Now remember again, number 1 to any power will give 1, which means that the derivative of this function will be n, or f prime of 1 equals n. So what that means again is that the value of the slope will be n. Therefore, we're going to say that the equation of the tangent will be 1 equals, so 1 is the y value here. The value of the slope is n times x, which is 1, and then plus b. So we have to find the value of b. So as you can see, we have n times 1 is simply n, obviously. And then isolate b by taking n to the other side. So the value of b is 1 minus n. Therefore, we're going to say that the equation of the tangent line would be y equals nx, so that would be n is the slope, x, and then plus the y-intercept, which is 1 minus n. So this would be just the equation of the tangent. Now that we have the equation of the tangent, we can look for the x-intercept of it. Remember that to find the x-intercept of any function, and remember that the tangent line is a function on its own, it's a linear function. So to find the x-intercept, we need to make y equal to 0. So we're going to use the equation of the tangent, which is y equals nx plus 1 minus n, and make the value of y equal to 0, and then solve for x. So let's continue. So we have n times x plus 1 minus n. Now we are solving for x, remember? So which means that the term nx should stay on the right side. The rest of the terms will come to the other side. So the negative n will come to the left side, become positive, and the positive 1 will come to the left side and become negative. So therefore, now we're ready to isolate x completely. So we'll say that x equals n minus 1 divided by n. So the x-intercept of the tangent line equals n minus 1 divided by n. So we have just found the x-intercept. So it's time for us now to take a look at the question to make sure that we have answered every part of the question completely. So what happens to the x-intercept as n increases without bound? So which means as n approaches infinity. So what that means is we need to figure out what would the value of x become as n approaches infinity. So remember that if we want to find the value of x-intercept when n approaches infinity, it means that we need to substitute the n by infinity. But if you substitute n by infinity, then we'll have infinity minus 1 over infinity, which is an indefinite value. It has an indefinite value because infinity over infinity is undefined, because we cannot compare, because when you divide, you just compare the sizes of the numerator with denominator, basically. So we cannot compare an immeasurable quantity with another immeasurable quantity. So in other words, though, we need to find the limit of this function as n approaches infinity. So in other words, we need to estimate this value instead of evaluating it. And to estimate it means to find the limit of it, since it is an indeterminate form limit. So we cannot substitute n right away, we said. So what we are going to do is factor out n. And we have explained this in the past, how to find limits at infinity. So if you need help with it, then you can always go back to the lesson. So we are factoring n from both numerator and denominator. In the denominator, n is the only term. And now it's time to simplify n. So, oopsie. So this will turn to the limit as n approaches infinity of 1 minus 1 over n. Now we can make n infinity, so 1 minus 1 over infinity. Now, 1 divided by infinity, you can estimate it, it's going to be 0 plus, which means that the value of this expression, which represents the x-intercept of the function, would be equal to approximately 1. So therefore, we're going to say that the x-intercept of the tangent as the power of the function approaches infinity will be equal to about 1. So with this, we've answered the second part of the question. So we found the x-intercept. So this is the x-intercept right here. And then we discussed what happens to x-intercept as n increases without bound by estimating this expression as n approached infinity. So by finding the limit as n approached infinity, and we found out that that was equal to 1. Now, the last part of the question is to explain the result geometrically. So I prepared actually the geometric explanation, which is basically the graphical explanation of this solution ahead of time. Let's see if it is saved in here. Okay, cool. So what we do in this case is we write the equation of the function f of x equals x to the power of n. Now, when you do so, you notice that the slider will pop up in here. So I set the slider actually from 0 to 100 so that we can see more of it. So I'm going to leave it here at 0 because that's kind of interesting. And then I wrote down the equation of the tangent line y equals nx plus 1 minus n. So this is the equation of this tangent line that we just found here. This is the equation of the tangent at 1, 1, right? So as you can see here now, as we change the value of n, and I'm going to let n be equal to 1. If n equals 1, this is f of x equals x. And the x-intercept of the tangent line is the same thing. So the slope here would be equal to 0. So we're going to continue with a power of 2. So as you can see in here is a tangent line drawn at 1, 1. The x-intercept of it is at 0.5. I'm going to make n equal to 3. So now we have a cubic function. Here is the tangent line at 1, 1. And you see that the x-intercept is at 0.667. Let's increase n now, and let's make it 6, let's say. And here is the tangent line again at 1, 1. And notice that the x-intercept is approaching number 1. I'm going to increase to, let's make it, leave it here at 31, which is an odd power. Again, at x equals 1, 1, you see that the x-intercept is approaching 1 again. So I'm going to increase the power to 100. Now, when you increase the power to, well, that was not, okay, perfect. So at 100, you see that at x equals 1, 1, now the x-intercept is at 0.999. So the tangent line will become almost vertical because as the power increases, the instantaneous rate of change of the function will increase very, very fast. So the tangent line will become almost vertical but never vertical. So the slope will never be undefined, but it will get very, very close to it. And the x-intercept will never be equal to exactly 1, but it will get very, very close to it. So I hope this explanation made sense, and thank you for learning with me. Bye for now.